The importance of electricity in our modern world can hardly be overstated. What was a luxury 100 years ago is now a critical component to the safety, prosperity, and well-being of nearly everyone. And yet electricity is so unlike our other physical necessities. We can't hold it in our hand, we can't see it directly, and we usually only have a vague understanding of where it comes from. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about power generation. Generation is the first step electricity takes on its journey through the power grid, the gigantic machine that delivers energy to millions of people day in and day out. We talked about the power grid in a previous video, but there's one crucial point that's worth repeating. It's a real-time energy delivery system. Electricity moves at nearly the speed of light, and current availability of large-scale energy storage is negligible. That means that power is generated, transported, supplied, and used all in the exact same moment. The energy coursing through the wires of your home or office was a ray of sunshine on a solar panel, an atom of uranium, or most likely a bit of coal or natural gas in a steam boiler only milliseconds ago. Because of the laws of thermodynamics, all our electricity starts as some other kind of energy, which means all our ways to generate electricity are just fancy ways of converting one type of energy to another. And in most cases, the type of energy being converted to electricity is heat. Take a look at any of the various pie charts showing the breakdown of global energy production. You'll see that the vast majority of methods we use to generate power are essentially just different ways of getting water really hot. Many thermal power plants, as they're called, use fossil fuels like coal or natural gas in a furnace to generate steam. These type of plants have the obvious disadvantage of producing tremendous amounts of carbon dioxide as a byproduct, a greenhouse gas that's largely responsible for the ongoing rise in the average temperature of the Earth's climate, also known as global warming. In fact, electricity production makes up about a third of total global greenhouse gas emissions. Luckily, there are other ways to generate large quantities of steam that don't rely on fossil fuels. Some plants use the fission of radioactive elements in a nuclear reactor as a source of heat. Some parts of the world can use geothermal energy, heat from inside the Earth's crust. We can even use arrays of mirrors to concentrate sunlight and create enough heat to run a boiler. But beyond that first step, thermal power stations are pretty much all the same. Once the steam is created, it passes through a turbine, which converts thermal energy into rotational energy. The shaft of the turbine is coupled to a rotor, that's the part that rotates of an AC generator, that spins a set of magnets. The stator, that's the part that's stationary, has a set of coils of wire called windings. As the magnets on the rotor pass each winding, they generate a voltage across each coil. In most places in the world, the number of coils in the stator is 3 because our grid is built for 3-phase alternating current. The benefit of having the current alternate directions is that it makes it easier to step up or down the voltage using a dead simple device called a transformer. The benefit of generating power in 3 individual phases is getting a fairly smooth supply of electricity that overlaps, so there's never a moment when all the phases are 0. A 3-phase supply can also carry 3 times as much power on 3 wires as a single-phase supply wire can carry on 2. This is why steam turbine generators almost always have coils grouped in 3. But steam isn't the only way to spin a turbine. Hydroelectricity uses flowing water, and wind energy production has seen massive growth in the past 10 years. The other renewable source of electricity that's seeing explosive growth is solar photovoltaic, or PV. The cost of solar cells, which convert light directly into electricity, has plummeted, making it feasible for homeowners and businesses to install them on rooftops and supply some or all of their own power needs. Large-scale solar farms are also popping up in sunny climates to meet the growing demand for renewable electricity. Being able to power the grid directly from sunlight without harmful byproducts is awesome, but it does come at a cost. Besides the obvious disadvantage of only working during daylight hours, solar PV has another disadvantage on the grid. It doesn't have any inertia. One of the biggest benefits of connecting lots of power plants together is the tendency of power to remain in motion on the grid, even during localized faults and disturbances. This inertia helps keep our electricity supply reliable and stable. But electricity doesn't have inertia on its own. You can't give the electrons a kick and hope they continue down the wires without any help. The inertia comes from the physical rotation of all those massive interconnected generators. You can imagine the power grid as a train going uphill. The locomotives work together to carry the load. To maintain speed, the throttle or number of locomotives needs to be constantly adjusted to match the load of the train, which represents the total power demand constantly changing throughout the day. The power grid works in a very similar way. Electrical demand is felt immediately by all the connected generators. Each additional demand causes a little more load on every generator together, slowing the rotation by just a tiny amount and thus decreasing the frequency of the alternating current. Similarly, if electricity generation exceeds the demand, the generators will speed up. You can see this demonstrated in a typical brushless motor, which is wired exactly like a three-phase generator. Under no load, the motor spins freely, but if I short the contacts together to simulate a high electrical load, it takes more energy to turn. Power consumers turn on and off electrical devices at will, with no notification to the utilities at all. So to avoid fluctuations in frequency, generation has to be constantly adjusted up or down to match electrical demands on the grid. This process is called load following. As demand on the grid increases or decreases throughout the day, grid operators dispatch generation capacity to match it. Going back to our analogy, the speed of the train represents grid frequency, 50 or 60 Hz depending on where you live. Every locomotive and every train car is designed to travel at exactly that same speed, and the stability of the entire system depends on perfect synchrony. If one part of the train starts moving faster or slower than the rest of the cars, things go haywire in a hurry. This is why inertia is so important. If any problem occurs, for example if one of the locomotives dies, the train has enough inertia to keep things moving while the problem can be addressed. It's also why grid operators maintain spinning reserves, generators that are ready to connect to the grid at a moment's notice. And before a generator can be connected to the rest of the grid, it needs to be synchronized as well. That means its frequency, phase, and voltage need to be perfectly matched with grid power by adjusting the speed and excitation of the electromagnets in the rotor. A special instrument called a synchroscope helps with this process. Once the synchroscope gives the all clear, plant operators can close the breaker to connect to the grid. This is a simplification of load following and generator dispatch, but it highlights one of the key differences between wind and solar and the rest of our generation capacity. If we want our lights to turn on right when we flip the switch, we have to understand that grid operators need the same thing. The expectation that generation capacity will be available on demand. Reliability is the overarching purpose of having an interconnected power grid in the first place, and incorporating unreliable sources of power like wind that depends on weather and solar that's only available during half the day is one of the biggest challenges we face with electrical infrastructure. Because of global warming, transitioning to renewable sources of electricity is one of the most important challenges of our lifetime. And I think that overcoming it starts with all of us being more interested, informed, and excited about understanding where our power comes from.